look at the work done by an external force. That is not conservative. And that's what we want to talk about right here. So what did we talk about up to this point? So now we've now expanded our system from 2 forces to 3 forces. So to conserve mechanical energy, only 3 possible forces can be in our system. So what do I mean by that? Well, I have a system, right? This is my system right here. And so when I'm looking at my system here, what you're seeing here is that everything in my universe has to be contained within the system. So when I look at my system here, we said that there could be 2 forces. We said that initially we said we could have a spring force, we could have a force of gravity, and now we've added a force and said we could have tension. But this tension can only be in such a way that the tension is perpendicular to the displacement. If this is true, the workings will keep energy as a constant of the motion. In other words, when I look at all possible situations here with how the system's going to adjust, when I look at mechanical energy, this mechanical energy, regardless of what iterations actually happen within the system, that will always be a constant. And that's exactly what we want. The question is, what happens if there are now external forces acting on the system? Right? What happens if now there are external forces working on a system? The answer is energy, mechanical energy, is not conserved. That means the total energy changes, right? This means it changes. And that shouldn't be a surprise, because we said that anytime there's a net work done, that work changes the energy. So in other words, if I start off with energy, it has to be like this here. So what I'm really saying here is that if I have a system, right, regardless of my system, if I have external work that's being done, there's two situations that could happen here. I could have work flowing into my system, right? Look at the network. If the network is positive, then the energy flowing into my system is then going to do what? This tells me here is that it increases E mechanical. On the other hand, if I have work that's being pulled out of my system, right? So now the network is negative, then what we're seeing here is that there must be a decrease in E mechanical. So I can change the mechanical energy of the system here. And so what I'd like to do here is I'd like to show you a video of a demonstration that's very popular. And it's the old bowling ball. And I'm sure you probably have seen this here. And one clear example of how I could increase the energy of the system looks like this here. So here's the example. This is of a bowling ball pendulum. And this is a class demonstration that I've been doing for, I mean, everybody does it actually, anybody in physics. And what you're going to do here is that typically what happens, at least in the classroom that I have, is that I have a chair. And when you're looking at this chair here, what I would do here is that I would put this up against a wall. Okay, so this would be a wall right here. And then I would sit myself down in this chair. So that means I'd be sitting here and I'm now holding a bowling ball right at my face. So in other words, I have a bowling ball right here, and then this is attached to, I'm going to actually bring this down a little bit. And so what you find here is that this guy is now tethered to a spot up here. So what's going to happen to the bowling ball? Well, the bowling ball, you can see it's going to go below the ground here. It's going to do this. It's going to come, it's going to swing. It's going to swing however distance is, wherever the distance that it's going to do here. And the question is, what actually happens? So what we want to do here is that the question is this. What happens if the bowling ball is just released with no push? Well, according to conservation of energy, we could then go in and do a bar diagram. What I'd like to do here is that I'd like to show you a video though, because if you have not seen this, this is quite spectacular. Let me go get this here. Okay. So this is a YouTube video, and you could see how he's holding the bowling ball. And this isn't the bowling ball, but it's a massive ball. I think it's probably of the order of, I don't know, 30 pounds or something, because it looks like it's just a big ball bearing or something. But let's see what he does here. So he's going to release it, and let's check this out.
3, 2, 1, go.
Oh. And what you're seeing here is that you're seeing what? you're seeing that the bowling ball does not reach his face here. I mean, it turns out that there's a little bit of friction right at the pivot, but the bottom line is that it comes down to this here. When you look at how we want to look at this thing, one of the things that we can do here is that we could set our height variable to 0 right here. And then what happens here, of course, is that we've now defined potential energy. So what happens? Here we go. So if I look at just the center of the mass, this is our potential energy. And when you're looking at the potential energy, since it's starting from rest, then this tells us here is that this is our total energy. That's a constant. So what actually happens? Well, if there's truly no friction in the system, when it gets to the lowest point, of course, that's where the potential energy is 0. Then we see here that it's all converted into kinetic energy. And then it's going to swing. And where is that ball going to go? It has to go by conservation of energy to the exact same height. So when I look at this thing here, I then reach this potential energy height where none of the energy is in the form of kinetic energy. And then what does it do? It then swings all the way back and it comes right up to his nose. But you saw that it actually was not at the same distance. That work turns out to be working that takes energy out of the system here. So now what we're doing here is that we want to go in and we want to go in. Oops, sorry about that. I just saw that Sean put in that one. And I have not looked at that one, so I'll have to look at that video in the future. So what I want to do here is that I now want to ask the question. So if, in this case here, if the external force is 0, then that means that the external work here is 0. Therefore, mechanical energy is conserved. In other words, when I look at the energy state 1 plus what the external force is looking like, since this is 0, we can then see that E1 is equal to E2. However, we want to ask a different question. What happens in his excitement if this person shoves the ball initially? Okay. What I really mean by this is in other words, that the external work here is not 0. Now, I'm going to get technical here. So you got to be really, really careful how you write this in the future in any quiz or exam here. Because when we push, so when we push a ball, this is work done by a non-conservative work. This is not a conservative force. Your body pushing generates heat that leaves energy out of the system if that person is considered part of the system. And so what you're finding here is that the work, done by this external force is then changes the energy of the system, but in this case, it changes the kinetic energy of the ball. So that means here is that if I start off at some location 0, at some kinetic energy that I'll label 0, the work of the push, which is a conservative force, then changes the energy of the ball to be at this one state here. So note, it's very common for people to say, oh, you added kinetic energy. No, you did not add kinetic energy. You did work, and that work changed into kinetic energy. So it is incorrect to say that you added kinetic energy. You did not. You did work, right? That's what we mean by a push. So what you're seeing here is that now, let's look at the pendulum bob here. So if I look at the pendulum bob, it's going to look like this here. So let's say that this is the pendulum bob, right? And then what I'm going to do here is I'm going to draw a nose. I'm not really sure how you draw a nose here, but maybe we have something like this. And of course, we need to color the nose so that we know exactly what we're looking at, right? So we're looking at that green nose. So then what is the pendulum bob going to do? So we know for a fact that this ball is going to do what? It's going to swing down. And as it swings down, it has to come up to the same height up to right here. So now we're looking at this scenario here. And then of course it's going to swing back and forth as it does this thing. So if I look at my situation here, let's say that I pick the ground here to be my 0 point here, right? So my ground here, because that's what we did before, we're going to say here is that this height tells me that that's 0 right there. So let's look at my system now. So if I look at my system, what is my system? My system has to be what? The ground, the string, and the force of gravity. But we already said that when I include these two forces, right? The force of gravity, the tension in the string, that those two forces will not change the thing. So if I look at the scenarios we already talked about, that means this bowling ball here has this amount of potential energy that we can account for. And then of course, when this swings back, we know for a fact that at this point right here, we know that the kinetic energy is 0. But now something else happens. I'm going to call this what? State number 1, state number 2 here. So now what I'm going to do here is that there's going to be external work now. That means this person is going to apply a push. So that force now adds energy to the system here. So when you look at my system here, we could see here is that this is external to the system. And the fact that the force and the displacement in this case, right, here's my displacement, are in the same direction means that that net work is now, right, is now increasing the energy of the system. So here I go. So if I redraw my situation, let's look what happens at state number 1. So state number 1 tells me I'm going to have this amount of potential energy to start off with, right? So this is my potential energy at 1. And what I'm doing now is that I do external work. If I do external work, that means I have now increased the total energy of the system. But wait a minute. Exactly at that same point, what really happens? I still have my potential energy here, but now that work has been converted into kinetic energy at that point. So what happens? The ball's going to swing. By the way, I should have had my line here just to make sure. I now have a new total energy. So from here, let me be careful here. Now there are only 2 forces acting on the system, right? In this case here, what do I have? I have the work of the tension and I have the work of gravity. Now, this total energy here is the new constant. It's a new higher constant energy. So then what happens? The ball swings out to point number 2. But now you can see here is that this guy's going to swing out to what? A higher height. I don't know about much higher, but there's a higher height. So then it's going to swing all the way back. And as it swings all the way back, when it gets there, what do we know? We know that this is the original height, right? This is our original height. So back at point 1, it's like this. And of course, now we know that there is kinetic energy here at point 1 again. No surprise, but note, why is that energy conserved? Because those are the only 2 forces doing work. And as a consequence, what ends up happening? Well, there's a collision, of course. And so when you're looking at this point, now what ends up happening is that now there has to be work done by the nose. And what is the nose supposed to do? It's supposed to stop the bowling ball. So therefore, that work by the nose takes energy out of the system. It may break the nose in the process, but that's what has to happen here. And so what you're seeing here in this example here is that so the work done by the push, which is external to the system, increases the total mechanical energy. So when I look at my system here, what I'm seeing here is that I'm seeing what? What I'm seeing here is that work done by the push, that increased the total energy of the system. So the work of the push increased that. It increased it. Okay, so as it increased it, what you're seeing here is that there's an increase in total energy. However, if I look at the work of the nose, that work of the nose did what? That work of the nose was also external to the system, and it decreased the total mechanical energy. And in this process, what you're seeing here is that now my system here, when I look at this, I am literally taking energy out of my system. And as I'm taking it out of my system, I'm looking at it moving, leaving the system here. And this would then be the work of the nose. So the question is, what do I mean by this? Well, look what happens. So if you're looking at the bar diagram, look what happens. I start off with this amount of kinetic energy, at point 1, I start off with that amount of potential energy. And then what happened? I did this amount of work that was the push. And you can clearly see that this guy increased the total energy of the system at that point. And the way it increased it is that we saw that it went from here, and then all of a sudden there's a step up in the energy. So we're seeing here that this is exactly what happened right here. So now that energy was converted into kinetic energy at that point. So we're seeing that this guy from here to here, this is clearly an increase. On the other hand, when we came back here to the nose here, what you're seeing here is that this was the potential energy at that point. And if you look at the kinetic energy at that point, it looked like this. So now, what did the work of the nose do here? Well, I was at a higher. And then what does the nose do? It stops the bowling ball. And in the process, you may bust your nose up pretty good, but you can see that there's clearly a decrease in the energy of the system. And so in this process here, you see that this is a decrease. So in this case, I started off with E1, and then I did positive network to increase the energy to here. In this case, I started at E1, and then what? I did negative external. You know what? I should not have said net. I should have said external. And that decreased my energy of the system. That's what I mean by that. So what I want to do here is that I want to go in and look at an example. Okay. And the example that I want to look at is something like this. So you know what? I should be really, really, really careful here. So just in summary, before I go to the example, external works change the energy of the system. And so when we look at this thing, what I'm really saying here is that if I have energy and I have a positive sign and I'm doing external work, then this implies that this is an increase in energy. If I have energy and I clearly see a minus sign here, then that means that this external work decreased the energy. So we have to pay attention to how is the force acting in the direction of the displacement. Is it with the displacement or is it against the displacement?